I know the communication between the systems between Pearson and Canvas isn't great, but I'm kind of lost on what's due when.
Oh, okay.
We're on chapter 20, so I think that homework is due next week.
Yeah, I pushed that back. I'll go on there now and double check, just to make sure, and that way we'll have it. Uh, there was a change I'd made some time ago, but I went yesterday and noticed it hadn't changed, so I had to go back and change 20. And it was specifically because you had told me
Oh,
about
okay.
trying to do 20. I was like, oh crap, and I saw it was really due way too early. I've now moved the chapter 20 homework to be due 223, which should be this Sunday.
Oh, okay.
That gives you enough time, but the 21 is this Sunday too, at least tentatively. That may change a little conceptual for chapter 21. Well, that's not right. Okay, there's a case where I must have changed it incorrectly. Conceptual for 21 had 18, and the conceptual for 20 was the 218 as well, both of which are today, so that's not right at all. Uh, I'm going to go ahead and make the chapter 20 and 21 due to on the 23rd. But if I see Thursday that I haven't made enough progress, then I will push these dates back a little bit,
Okay.
at least for chapter 21. But chapter 20 is going to stay due on the 23rd.
Okay. Got it.
Okay.
And then, yep. And then there's an online test next week, due next week, I guess.
Yes,
Right?
actually, it's
Okay.
due. I went ahead and opened it up last night. It'll be due this coming Monday, for your class, because your class, in my record, sort of meets on Tuesdays.
Sure.
So you're supposed to have it done by 11:59 p.m. Monday of next week, or yeah, Monday of this coming weekend.
All right. Yep. Sounds good.
No problem. Okay, so I got that part done at least. All right. Well, it's definitely time to get started. It's well after 5:20, at least 2 minutes after, so I'm going to go ahead and get started. We had talked a little bit about charge. Specifically, I had talked about charge and uh, some of the conduction ideas, what makes a conductor, what makes an insulator, and how it's really more of a spectrum of values of conductance, so that, in some realms, what you would consider a insulator in other realms could actually be specifically considered a conductor. And that's just because it depends on how much voltage you're dealing with. For instance, if you're dealing with 3 million volts, then air is a conductor as long as you're not trying to go a distance any further than 1 meter. But if you're talking much smaller voltages, which is much more normal, of course, then you can use a lot less distance for air. But conductors, like copper, aluminum, gold, silver, basically the metals are all decent conductors. But, if you're really trying to put a ton of amperage through something, you might find that even that's not conductive enough, and in some sense they're acting as insulators. Uh, then you might want, for instance, superconductors, which we don't really talk about so much. I mean, your book makes mention of them, and then once we get to quantum mechanics, you can learn a little bit more about why they work. But the main thing is with superconductors, they, as best we can tell, seem to have zero resistance. Not really small. I'm talking zero resistance, and you could make, in some sense, almost like perpetual motion type machines that come close to violating the second law of thermodynamics and stuff like that. But the main thing is, I'm going to leave all those impressive examples and the videos, for instance, from the MIT group that I've put on my Canvas page. I'm going to leave all those videos and stuff to you for you to look at, so you can learn, how do we actually polarize something? How do we induce a charge in it? How do we actually make it charged as opposed to just polarizing it? That kind of stuff. All that stuff are good concepts, but we really don't have time to teach them so much in the lecture portion when we have so many problems to solve. So I'm going to jump right in and start covering Coulomb's law, and I'm going to give you a little bit of the information that you want to make sure you know. So let's go ahead and share my iPad screen real quick. Okay, so the iPad screen should come up. There's a ton of writing on this first page because I just wanted to put in words exactly what Coulomb's law is and how it's stated and stuff of that sort. But I also, while doing that, I went ahead and decided to write down some other things. So you're looking at them now. I know my handwriting's not necessarily the best, but what it says is Coulomb's law. The electric force, also called the Coulomb force, is directly proportional to the product of the two charges and inversely related to the square of the distance between the two charges. If the charges have the same sign, meaning plus and plus or minus and minus, the force is repulsive. If the charges have unlike signs, the force is attractive. Finally, the Coulomb force acts along the line connecting the 2 point charges Q1 and Q2. If Q1 and or Q2 are not point charges, the center of charge must be found for each, and the force acts along the line connecting those centers, and the distance R12 is the distance between those centers. This can actually be written in equation form as F is equal to K Q1 Q2 over R12 squared. And I just subscripted the R12 just so you know that that's specifically the distance between object 1 and object 2. If they were point charges, then it's just the distance between Q1 and Q2. If they were not point charges, it's a distance from the center of mass of Q1 to the, or excuse me, the center of charge of Q1 to the distance or to the center of charge of Q2. So the distance between them is from center of charge to center of charge, or if they're just point particles, it's from point particle to point particle. In general, for instance, we sort of have to treat an electron as if it's a point particle because we've searched for its physical dimension and gotten, last I checked, it was like I want to say it was like 10 to the negative 16th or 19th or some god awfully small quantity, way, 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 way smaller than the nucleus. And even then, we know that it's smaller still. So right now, we treat an electron as an elementary particle, meaning it's not made of other stuff, and as a point particle because it appears to have no physical dimensions. Okay. In that equation, of course, the K that I wrote was 8.988 times 10 to the ninth Newton meter squared per Coulomb squared. What you will discover, though, is it's much more common to use Q1, Q2 over 4 pi epsilon naught R12 squared. Huh. When we're using that, though, the epsilon naught is 8.854 times 10 to the negative 12th, and that unit, of course, is Coulomb squared per Newton meter squared. So you can use either one of those. I think you'll find, at least in this opening chapter, it's a lot easier to use the 8.988, but later on, none of your equations are going to include the K, so you need to go ahead and get used to using 1 over 4 pi epsilon naught as well. You also need to know what makes a material a conductor or an insulator. I mentioned to you that basically a loose tether on your outermost electrons is what makes things that we consider to be conductors. And again, it's still sort of a spectra or a continuum of conductances that make, in some cases, what other people would call a conductor, some people might call an insulator, and vice versa. So, the main thing is that a conductor in general should have a loose tether on at least its outermost electron, and an insulator should have a stronger pull on the outermost electrons of those type atoms or molecules. You should know that charge is conserved. That's a absolute fundamental law that we have so far. Unlike conservation of mass and conservation of energy, which we sort of thought were 100% absolute until Einstein came along. Excuse me, until Einstein came along and gave us E equals mc squared, and then it became obvious that in fact mass can convert to energy, and energy can convert from energy to mass. So now we have to say mass energy, mass hyphen energy is conserved because you have to take account of both of them in order to see a conservation law. But the charge being conserved, we haven't found any such breaks in that. We know that, if the total charge is positive 27 E before some event, then the total charge of all the parts that left that event are still around either one should give you plus 27 E again. So, and we've never found a contradiction to that. We also found that in terms of the smallest fundamental charge that is actually fairly stable, that turns out to be the charge of the proton and the charge of the electron, which are equal in magnitude but opposite in sign. And it's 1.602 times 10, it's actually 1.6022 times 10 to the negative 19th coulombs. Coulomb is a big unit of charge. I wanted to mention that just because you'll find out later that in some calculations and therefore in some realities, in other words, some real cases, not some realities, but we've discovered that a single lightning strike sometimes only delivers on the order of 100 coulombs. So, 100, 200, maybe 500 or 600 coulombs is all that's being delivered from a, lightning bolt. That's pretty impressive. So, yeah, the unit of charge called the Coulomb, which is abbreviated capital C, that is a big unit of charge. I also wanted you to remind you that basically there's some very important bold-faced terms in all the chapters, and generally speaking, unless it's a subsection that I've skipped, all of those are important. But I want to let you know that in this chapter, those are important as well. But you want to make sure you have an understanding of what static electricity is, what an ion is, what it means to be a polar molecule, what is neutral, what is a semiconductor, what are free electrons, what's charged, what's induced, what's grounded, what's electroscope, and all other bold type-faced terms in this chapter. Okay. So definitely check out those videos that I shared for you guys to look at. For instance, Tesla coils and Van de Graaff generators. Those are the things that you've probably seen where people will put their hands on top of it and then their hair will stand up. Uh, that I did that one too many times. That's where my hair went. Not really, obviously, but anyways, so let me get started with using Coulomb's law now that I've explained it to you and give you some of the background material. The first example we're going to deal with is the hydrogen atom, and it says the hydrogen atom consists of a proton of charge E equals positive 1.602 times 10 to the negative 19th coulombs, and an electron of charge negative E. So, in other words, negative 1.602 times 10 to the negative 19th coulombs. On average, the electron, I forgot to cross my T there. On average, the electron and proton are separated by a distance of A0. That's called the Bohr radius, and it's 5.292 times 10 to the negative 11th meters. Since the proton is positive and the electron is negative, is the Coulomb force between them attractive or repulsive? So that's a question you should be able to answer. Hopefully, you know the answer to that. We'll address it in a second. And then the other part is on average, how big is that force in newtons? So I'm going to do that calculation. I will tell you there is an extra credit problem you can do where you do the same calculation for hydrogen for the electric or Coulomb force, and then you do it again for the gravitational force, which you might call the Newtonian gravitational force, using a very similar equation. And then you're supposed to take the Coulomb force divided by the gravitational force, and that'll give you an idea of how much stronger the electric force is than the gravitational force. That's an actual calculation you can turn in for extra credit. So let me go ahead and get started with this. And so the solution will require our use of the Coulomb law, or Coulomb's law, which is F equals K Q1 Q2 over R12 squared. I'm going to call Q1 equal to E. And I mentioned this before, but I want to reiterate it. When I use Coulomb's law, I do not put the signs in with the charges, and I don't want you to do it. Yeah. I don't want you to do it either. It only makes problems. Okay, so what your use for this equation is you're going to find the magnitude of a force by plugging it in. And then you're going to decide on a case by case basis whether that force is attractive and which particle you're thinking about it acting on. Because if it's acting on a particle and it's attractive, then you know the force should point from that particle towards the other particle. If it's a repulsive force and you're thinking about a particle, then the force should be acting on the particle that you're looking at as if it were or originated at the other charge. So that's part of it you've got to work on. The Q2 would actually also be E, but in this case it should be negative. So I'm just going to write it as E because I don't put in the signs. Okay, so it's technically correct to say one is positive and one is negative, but I'm not going to put them in the signs. So I had a little bit of a philosophical conundrum when it came to whether I was going to write Q2 equals negative E or Q2 equals positive E or Q2 just equals E. I'm going to say R12 is equal to 5.292 times 10 to the negative 11 meters. And the first question, A, since these charges, one being an electron that's sort of acting like it's orbiting around the nucleus of the atom, and the other one being the nucleus, which in the case of hydrogen, at least the simplest of hydrogens, is just a single proton, and that one's positive. So you've got a negative electron orbiting around a positive proton. That means they're unlike charges, and unlike charges attract, so it should be an attractive force. I should also say that that sort of picture of the nucleus with orbitals around it for the electron, that's called our planetary model of the atom. And it's like the planetary model, and there's a lot of consistencies with the planetary model. Like for instance, the math. Yeah, I swear I've not yawned all day, and it's like as soon as I start this, I started yawning. But for instance, the sun makes up about 99.99% of our entire solar system, and the nucleus of the atom makes up about 99.99% of the entire mass of the atom. So, in that sense, they're very similar. Also, the distances relative to the size, so the distance from the center of the nucleus to the center of the electron at a particular instant in time, in some sense, is way, 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 way bigger than the dimension or the diameter of the nucleus itself. So that also is very much like our solar system in that our sun is quite big, but still very, very minuscule compared to the orbits of the planets around it. So that's another way to keep it or to compare it to the planetary model. The main problem with the planetary model of the atom was that Maxwell's equations, which we're getting ready to learn about, taught us that anytime a charged particle accelerates, and remember, acceleration means you're either speeding up, slowing down, or changing direction, or some combination thereof. So even if the electron were orbiting the atom at constant speed, it's still accelerating. And because it's a charged particle accelerating, it would have to give off energy. We call that radiation, or it's radiating. And a quick calculation would show that even hydrogen, which is the most prevalent element in the universe, even hydrogen atoms would only last on the order of a millionth or maybe even a billionth of a second. It's been a long time since I looked at that calculation or looked it up, but I think it's on the order of a millionth of a second. So we know that can't be true because hydrogen is actually quite stable. Not only that, the orbits, of course, for the electrons in the planetary model would be going around in every which way, which is other than which I should say is different from the planetary model in that all the planets sort of stay more or less in one plane, but the electrons can do quite a bit different. Now, what Bohr ultimately does when he, wins his Nobel Prize was he said, well, we do have this problem that electrons would seem to radiate if they're orbiting. But he said, well, imagine if they happen to be standing waves, like if you take a slinky or a rope, you and another person, and you shake it against the wall, you get one hump up, and then on the way back, you get one hump down. and then one hump up and then one hump down. You just go back and forth like that. If you do it a little more rapidly, then you'll get half of the string as a hump up and the other half of the string as a hump down. And then the next second they reverse and it's hump down, hump up. So you have like two lobes. And then if you do it a little faster still, you get three lobes and then four lobes and then five lobes. Uh, those are what we call standing waves. So what Bohr imagined was imagine the electron uh, being a standing wave such that the distance around the orbit had to be exactly one wavelength or two wavelengths or three wavelengths or four wavelengths, but nothing in between. And when he did that, he was able to get the energy differences between orbitals of electrons to be exactly equal to the energy that you'd expect based on Planck's famous E equals h nu, which is h times the frequency formula. So it actually predicted the very data we already knew hydrogen was giving, which also matched a formula that a mathematician had given us for those colors that came out from the spectra of hydrogen. And for that, obviously, he won the Nobel Prize. But the cool part was he got exactly the same equation, only now instead of having what seemed like random numbers that someone had curve fit, now those quote unquote random numbers turned out to be actual formulas that involve stuff we knew of, like the charge of the electron, the epsilon zero, the speed of light, that kind of stuff. Bohr radius, which again was a list of other constants. So it was very, very important. Now we're going to go ahead and show you how to use the Coulomb formula, and that is as follows. Even though I didn't label them part A and B, we're just going to apply the formula. I'm going to put the numbers in with their units so you can see exactly what happens to everything. So 8.988 times 10 to the ninth. Notice that's a factor of a billion, whereas if you looked back at the Newton's law for gravity, you got F equals G M1 M2 over R12 squared, where G was equal to 6.67 times 10 to the negative 11th newtons meters squared per coulomb squared. So, or excuse me, per kilogram squared, not per coulomb squared. So you can see one's a factor of a billion and the other one is a factor of zero followed by a decimal point followed by 10 zeros and then a 667. So you can already tell that the gravitational force has to be at least 10 to the 20th bigger. Or I should say the Coulomb force has to be 10 to the 20th times stronger than the gravitational force. So now going back to finishing this calculation, this unit was Newton's meter squared per Coulomb squared. Now I've got to multiply that times the charge of the electron, which is 1.602 times 10 to the negative 19th coulombs. And then the other one, of course, is also 1.602 times 10 to the negative 19th coulomb. So you again see that I do not put the signs in. Okay, I don't put the signs in. Now I've got to divide that by the square of the distance between them. And on average, the distance between them is 5.292 times 10 to the negative 11th meters. So I'm going to square that. You can now see that the square of the meter is going to cancel out with the square meter, and you're going to see that the coulomb cancels out with 1, and the other coulomb cancels out with the exponent of 2, say. So you're only left with units of newtons. Now, when I do this calculation, I get 8.988 times 10 to the ninth times 1.602 times 10 to the negative 19th. That number I'm just going to square. And now I'm going to say divided by 5.292 times 10 to the negative 11th. And now I'm going to square that number as well. And that gives me 8.236. Oops. Switch colors for a second there. Ooh, I did not mean to do that either. Uh, Wanted this color. And I didn't want that. So, all right. So I get 8.236 6 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the negative eighth newtons. So obviously we were using 4 sig figs on just about everything. Yeah, in fact it was 4 sig figs on everything, and I got 4 sig figs out, so that's the appropriate number of sig figs, and that's it. Anybody have any questions with that calculation? Okay, that should be pretty straightforward, and I just wanted you to see that so you could see what I meant when I say, I don't actually put in the signs. I wanted you to see what it meant, how the units canceled out. I wanted you to see that I have to put in, for instance, units of meters, not centimeters, and that sort of stuff. So that's the main reason we did that. Now, you can take that same information and you can try the extra credit. I just gave you Newton's law of gravity, and also to help you with that extra credit, I'll tell you that the mass of the electron is 9.109 times 10 to the negative 31st kilograms, and that the mass of the proton is equal to 1.673 times 10 to the negative 27th kilograms. The neutron is more or less the same thing, except instead of a digit of 3 there, it's a digit of 5. So you can see the neutron's a little heavier, but we're talking about hydrogen 1, which only has a proton and no neutrons. Okay? Any questions on that? All right. So now that we've done a straightforward example of how to solve or how to use Coulomb's law with no vectorness associated with it, we now have to deal with the vectorness of the equation. So let's do that. And then we're going to deal with something else, specifically a way of dealing with what this is. This is action at a distance, because as you just saw, we had a proton sitting, say, here, and then an electron over here. No connection between them. There's nothing, no kind of ropes or strings or anything like that coming off the proton and touching the electron. Yet somehow a force magically is pulling on that electron to keep it in orbit. That's what we call action at a distance. And when Newton conjured up his idea of gravity, he knew that was an issue that he couldn't really understand how it could be, but he knew that he could solve physics problems with it, and just kept it. So ultimately, later on, we discover a very similar law with Coulomb's law, which actually there is some discrepancy as to whether it really should be called Coulomb's law or Franklin's law, or I want to say the other guy was Poisson or Laplace or somebody. There's a third person, all of which Ben Franklin and Coulomb and this third person, all of which had some claim to first discovery of that. They had all worked on the same sort of formula before, but Coulomb did publish it first. So, but I just like that little tie-in with Ben Franklin. That's kind of cool. All right, now that we have that, let me show you an actual problem where we're going to have to deal with the vectorness of it. So this is not unlike an example that your textbook has provided. I'm calling it example 2. And in this example, what we're trying to figure out is calculate the net electrostatic force on Q3. So they want us to calculate the total force on charge Q3. Okay. And I'm going to call that total force F3. Okay. I'll do that for a reason, and you'll see it in a second. There's a very typical terminology and suffixes and subscripts or whatever that we put on force symbols, and I want you to learn that. So that's what I'm going for. We'll explain that in a second after I start doing this. So I'm going to go ahead and draw a coordinate system, because we need to actually have some particles at very specific locations in order to solve this problem. So there's my y-axis. This is my x-axis here. Right at the origin, there is going to be a charge, and this charge is going to be called Q2, and Q2 is going to be a charge of positive 50.0 microcoulombs, and then a distance of 52 centimeters to the right is going to be another charge. In this case, this charge is going to be a positive charge, so I'll make it a different color. And that charge is in fact Q1, and that charge is negative 86.0 microcoulombs as well. And then 30 centimeters up along the y-axis, let me go ahead and write this 52 centimeters. So this would be 52.0 centimeters. And this one will be 30.0 centimeters right here. Now, this one's also going to be a positive charge. And this positive charge is big Q3 that I just mentioned to you. Actually, I think I want to put it down a little bit. I'm going to put it right here. So this is charge big Q3, and that one's positive 65.0 microcoulombs as well. Okay. Your book also gives us in this particular problem the diagram. It gives us the distance between Q1 and Q3. And you could, of course, figure that out on your own. And you should, because that's the way the problems will be given to you on the practice tests as well as in the tests and the midterms and final exams. You're not necessarily going to be given anything but the 30 and the 52 because that's really all you need. But if you use the Pythagorean theorem, you would find out that, in fact, this dashed distance is 60 zero point zero centimeters, and that this particular angle right here is 30.0 degrees. Okay, so that's the problem that we want to solve, and specifically, we want to calculate the force on charge 3. I actually was supposed to write the word net in there. I don't know how I didn't, but I will put it in now. So we're going to say net force on Q3. So here's my solution. So for starters, I've got to use Coulomb's law. So I know F is equal to K Q1 Q2 over R12 squared. I also need to know, of course, various distances. So I'm going to say R1, well, let's say R31. R31, and you'll see why I'm saying 31 instead of 1, 3. R31 is the distance between Q1 and Q3, and of course that is 60.0 centimeters. R23, or excuse me, R32 is the distance between Q2 and Q3, and that one, of course, is 30.0 centimeters. Now, in principle, you wouldn't necessarily have to know this to calculate the force on Q3, but still, I'm going to give it to you because it's on the page here, and that would be R12, in this case, is 52.0 centimeters. Okay, so we have that. We also have that Q, well, let's make it lowercase because that's the way I did it on the diagram. Let's have Q1 is equal to negative 86.0 microcoulombs. Q2 is equal to positive 50.0 microcoulombs. And Q3, that's actually supposed to be a capital. Q3, I'm going to put a little further over here, is equal to positive 65.0 microcoulombs. Now I also need a statement of how we're going to combine forces. Now there's basically a principle that we learned in chapter 4 and chapter 3 that basically forces are vector quantities and you add vectors vectorially. So if you want to know F3, which means the net force on object 3, then that is given by F3 vector is equal to the force on 3 due to 1. So notice I subscripted that 3, 1. That's the subscripts terminology that I'm telling you you need to know. So when we have two subscripts on a force, that means the first one is the object experiencing the force, and the second subscript is the object that's causing the force. So F31 should be read as the force on object 3 as a result of object 1, or the force on Q3 due to Q1. And then we also have to add the force on 3 due to 2, and that's called F32. So what we have to do is one by one calculate the magnitudes of these forces using the Coulomb formula, but then using the Coulomb formula and description, we have to figure out exactly, what these vectors are in terms of their magnitudes and directions and which way they point and all that good stuff. So we know, for instance, that F31, since we can treat 3 and 1 as point charges, F31 has to be along the line that connects Q3 and Q1. So along that dashed 60.0 centimeter line. Similarly, F32 has to be along the line connecting Q2 and Q3, so that's parallel to the y-axis, either up or down. We haven't decided that, nor have we decided whether the force F31 points up and to the left or down and to the right. We haven't done that yet either. But first, we're going to just calculate the magnitudes as follows. So I'm going to say F31 in magnitude is equal to 8.988. This time I'm going to leave the units off because you saw how they work out. You should be checking them in your head every time you do it, but 8.988 times 10 to the ninth. Of course, that's Newton meter squared per Coulomb squared. And then I've got to take the charge of Q3, which would be 65.0 times 10 to the negative 6. That's in coulombs. And then the Q1, which is 86.0 times 10 to the negative 6. Notice how I couldn't use micros and all that good stuff. I was supposed to use the SI base units. Okay. And then finally, I've got the distance between them, which is 60 centimeters, but we have to put that in meters, so it's going to be 0.600 meters. And then, of course, that distance has to be squared. I forgot that I had told you guys I would not be putting the units in there, and I accidentally put the unit for the distance in there because I was telling you it was in meters. So just want to point that out that it is supposed to be in meters. Now, if you look at this, if you remember what the units for 8.988 times 10 to the ninth were, you see that this does give just the units of newtons. And I always carry a couple extra sig figs just in case. So what I'm going to do is I'm going to take 8.988 times 10 to the ninth times 65 times 10 to the ninth, or excuse me, times 10 to the negative 6, times 86. Again, notice I'm not putting any positive or negative signs in here. I'm just treating everything as if it's positive. So this is 86 times 10 to the negative 6. And then I'm going divided by zero point 0.6, and this time I'm going to square it. And that gives me 139.5. Now, here I had 3 sig figs, so I'm going to carry 2 extra. I'm going to say 139.56 newtons. And remember, in my class, you can put extra digits on there, just underline them so everybody knows that they're not significant. So that's the magnitude of the force between between Q3 and Q1, specifically F31. What we're looking for is the force on Q3. So is the force on Q3 attractive or repulsive? Can you answer that for me? I'm going to put up the chat in case anybody's typing that. So again, the question is, in this diagram, I've got Q3 and I've got Q1. You can see the sizes of the charges and their signs, and I'm asking you, is F31 an attractive force or a repulsive force?
Attractive.
Yep, that's right. And Matt answered that as well. Because they're unlike charges, they're attractive. Now, what that means is the force acting on Q3 should be an arrow that points from Q3 towards Q1. So that tells us right now, even though it doesn't line up with any particular axes, that tells us that the force F31 points this way. Okay, so I left it as a black vector because I haven't broken down the components to X and Y components, which, is what we have to do when we actually add forces. So this is F31 right there. So that helps us. Not only that, we can realize that since this 30 degrees is between the horizontal x-axis and the dashed line, then if I draw a horizontal dashed line here, then this angle between that horizontal line and this same hypotenuse is also 30.0 degrees. That can help me better figure out what my components are. So I know, for instance, that the x component points to the right because I need to be able to navigate from the tail of the vector to the head of the vector by going parallel to the x-axis and parallel to the y-axis, or in the opposite order, parallel to the y-axis and then parallel to the x-axis. In both cases, you see my left-right motion was to the right, my up-down motion was down. So we can see that the left-right, it points to the right. That means the x-axis or the x component is a positive component, and I've been using green or red for positive components. So I'm going to go ahead and change my color to green, and I'm going to say this is the positive x component of F31. Notice it's supposed to be like a shadow of F31 cast on that horizontal line. Now I also have a negative Y component, and that's going to be drawn downward and in red because red, like a stoplight, is what I consider negative. So this is F31Y, and the green one was F31X. So we've got to figure those out before we can actually add them together. I can see from taking my trig functions that the sine of 30.0 degrees, which is opposite over hypotenuse, would be F31y over F31, the hypotenuse, and the cosine of 30.0 degrees, which is adjacent over hypotenuse, that's going to be F31 sub x over F31. So we can say F31 sub x would be the magnitude, which we got 139.56 newtons, and we decided that that one's positive, so I'm going to force this positive on here. This is the way I do my vector stuff. I do not want my trig functions deciding whether my signs are positive or negative. I want you to do the same thing. I want you to use your logic and your mind to figure out whether the components are positive or negative. And in this case, according to the second formula I wrote down involving cosine, I just have to multiply that magnitude times the cosine of 30.0 degrees, which again gives me 3 sig figs. So I'm going to say 139.56 times the cosine of 30, and that gives me 120.87. So this is going to be positive 120.87 newtons. And now I can also say F31y, according to the first equation I wrote, which involves sine. This one's going to be a forced negative. The magnitude is still going to be 139.56 newtons. But instead of multiplying by cosine, we're going to multiply by the sine of 30.0. And of course, if you know these angles off the top of your head and what the sines and cosines are, you can do that, but it's not necessary. So in this case, I'm taking 139.56 times sine 30. And this gives me negative 60. Again, the negative was something I forced, but it's going to be negative 69.7. Now that's my 3 sig figs, so I need two more is what I've been planning on doing. So this is 8.2 newtons. So that's my Y component of F31. Now I got to do the same thing for F32. So first let's calculate the magnitude of F32. The magnitude of F32 is 8.988 times 10 to the ninth. Again, I'm checking the units in my head and they're all working out. This time I have to have the charge of Q3, which is 65.0 times 10 to the negative 6. And I have to have the charge of Q2, which is 50. So that's 50.0 times 10 to the negative 6. In this case, both of these charges are positive, so I've got to keep that in mind as well. But now the distance between them is 0.300, and that's got to be squared. So when I do this calculation, I get 8.988 times 10 to the ninth times 65 times 10 to the negative 6 times 50 times 10 to the negative 6 divided by zero point 0.3 squared. Again, 3 sig figs is the limiting factor here. This time, because they're so close, the force is actually quite a bit larger. The magnitude turns out to be 324.57 newtons, and 3 sig figs means the 5 and the 7 are not significant. Now, can someone tell me, is the force F32, the force on 3 due to 2, is that attractive or is that repulsive?
Repulsing?
Yes, that's right. It's repulsive because they're both positive, and that means the force on Q3, should that act in the upward direction or should it point in the downward direction?
Up.
Yes. Okay. And it's actually quite a bit bigger in magnitude than this one, so I can't even really show it on the graph. I'm just going to say it's straight up like this. And notice it's already parallel to one of the axes, so I can go ahead and color it. And that's F32. Okay, so you can see that that force actually points up. In fact, its whole magnitude is the Y component. So now I'm going to write down that F32 sub X is equal to 0.00 newtons, and F32 sub Y is a positive 324.57 newtons, like that. Okay. So we can now use our other equation, which basically said that F3 is equal to F31 plus F32. And when we add vectors, we really are just breaking them down into x and y components according to whatever axes we chose. And then we're adding x components to x component to get the new x component. Then we're adding y components and y component to get the new y component. And that's our final vector. We can do that all with i's and j's and k's, and that's what I'm going to do first, and then I'll actually get the magnitude and direction. So we can see that the x component of F31 is 120.87, and the x component of F32 is 0. So the x component is just going to be 120.87 newtons, and that's going to be in the I hat direction. And notice it was positive. Now I have to add 324.57, which is the positive y component of F32. I'm going to add to that a negative 69.782, which is really only good to one decimal place. And in fact, the other one was only good to 0 decimal places. So really, we have to round it to the nearest whole number when I do this, but 324.57 plus negative 69.782 is 254.78. So it's going to be plus 254.7. It was 788, which I'm going to round to 79. And we realize, of course, it's only good to the nearest whole number. So only the 4 is a sig fig. And then I'll put a j hat after it like that. So that is the vector. Now I'm going to render that vector in 3 dimensions or in 2 dimensions so that we can get the magnitude and direction. What we see is we have an x component that's like 121 and a y component that's like 255. So it's more than twice as big. I'm just going to write it like this. I'm going to say we have a vector that goes to the right, and that magnitude is 120.87. And then we have another one that goes up, and that one's about twice as big. It's actually a little bit more than twice as big, and that one's 254.79 newtons. So what we ultimately get here is a vector that goes from the tail of the 120 to the head of the 254, and this is the F3 vector. And this angle right here is what we'll call phi, and obviously I can say F3 using the Pythagorean theorem. F3 gives us the square root of 120.87 newtons squared plus 254 plus 79 newtons squared. And then we've got to add them, take the square root. When I add 120.87 squared, what I see is that 120.87 squared gives me 100 or 14,609. So only the thousands place is good there for sig figs. That means the tens place and the ones place and the decimal places are all not significant. When I add the when I square the 254.79, when I square that one, I get 64,917. Again, 3 sig figs was what was accurate, so we're only good to the nearest thousands digit on this one as well. So I can add the 64,917 plus the 14,609.5569 if you really wanted to. And when I add those two, I know it's only good to the thousands place, so I'm going to write, oops, might want to write it with a pen as opposed to a laser pointer. I'm going to write it as the square root of 79,527.5 newtons squared under the square root. Now, as I said, the thousands digit is the last sig fig, so that means the tens digit's not, the ones digit's not, and the tenths digit is not. So we are going to get 3 sig figs out. That's the main thing I was searching for there. I'm going to take the square root of this value, which is the same thing as raising it to the 0.5 power. So doing that, I get equal to 282.01 newtons. That carries my extra sig figs as well. So the magnitude really is 282.01. I could also figure out that phi is equal to the inverse tangent of opposite over adjacent. So that'd be 254.79 over 120.87, which gives me again 3 sig figs. So if I take the arc tangent of 254.79 divided by 120.87, That gives me 64.62. Let's call that 621 degrees, and that gives me two extra sig figs. So one of our answers that we could state is F3 is equal to 120.87 newtons I hat plus one, or excuse me, plus 254.79 newtons J hat. But another one we could state as well is F3 is equal to 282.01 newtons. And notice this angle is measured up from the positive x-axis towards the y-axis. So that's in standard position. So we can just call that angle 64.62 degrees. So another answer is this. Anybody have any questions on that?
No. Yeah, well, one question.
Yeah, go for it, Matt.
Um, when you resolve the force on three due to one and the y component, the negative,
hmm
is that just intuitive because
Uh,
you know it's
it's intuitive to me, but I've tried to put it away, or tried to explain it in such a way that it should make some physical sense. So what I tell my students to do, and hopefully this will help you, is you knew F31 was going to be along this line. That's why I took the time to write out Coulomb's law in that sentence form, because it's got to be along the line connecting Q3 and Q2, or Q3 and Q1 in this case. So you know it's along this dashed line because that's the line that connects Q1 and Q3. You also know that it's attractive, so that's why you know it points this way, because it has to be attracted to Q1, which means it's going to walk towards Q1. So that put it that way. Then what I do is I just imagine walking from the tail of F31 to the head of F31, but by doing so, not go along F31, but by going along its components. So if I wanted to go to the head from this spot right here, I can choose to go left and right first or up and down first. If I choose left and right, then I see I have to go to the right, and the right is a positive direction. So that's why I put that there. And then I have to go down, and down, according to this, is a negative direction. That's why I put it there. Now you might say, well, I would have put my, component vectors the other way, in which case you would start here again, but you would first go down. Well, that's the negative of the y direction. That gives you that y. And then you'd have to go right. And that, of course, is the positive x direction. That gets you that plus. Does that help you, Matt?
Yep, thanks. Got it.
No problem. Yeah, that's that often is a concern of people's, and I don't. I hope that way works. Anyways, I've been telling them that for a couple of semesters now, and I think that works. But let me know if you find some other way that's more comfortable for you. Now, we have to address the bigger concern, and the bigger concern is sort of going back to what Newton said. You know, Newton said, "Hey, I've got this really cool equation for gravity, and it works, and I can use it to figure out why things are in orbit. I can figure out that, in fact, the orbits have to be conic sections, so you can only have an orbital that's either a circle, which is a special case of an ellipse, or it could be a parabola, or it could be a hyperbola, basically one part of the hyperbola, or something like that, or it could just go by completely straight with no deflections whatsoever, but that's only if it went really, really fast and was really, really far away. He was able to prove that, and in fact, he was even able to prove that mathematically there's only two forces in nature that would allow closed orbits. One of them is 1 over r squared, which is what a Coulomb and gravity law is, and the other one is F equals kx, which is what Hooke's law is. So it's really impressive what he was able to do, but we still have that fundamental problem. What is this action at a distance? So to deal with action at a distance, I'm going to explain it to you this way. So action at a distance resolved. So what we have is F is equal to, and we can just continue to use K here because it takes a lot less writing than 4 pi epsilon naught. But I'm going to do, instead of a Q1 and Q2, I'm going to call it a Q and a Q, and I'm going to say R squared like that. So one of the things we can think about doing is we can say, okay, well, maybe, yeah, the force is gotten by multiplying Q times K overall, and then dividing that by R squared. But maybe we can say that the charge big Q causes a disturbance in space. So imagine big Q causes a disturbance. Whoop, I realize that word is not going to fit in there. ANCE in the space around itself. Okay. That space around itself we can call a field. And in fact, we're going to call it an E field. That space will be called an E field or electric field. So you've probably heard these terms at least from science fiction books and or movies. But mathematically, what a field is you imagine that any area, any part of space, whether it be real space or whether it be some imaginary space that you made up that's made of, instead of distances, it's made up of other weird quantities like I don't know, velocity to the x direction and velocity in the y direction and velocity in the z direction or something like that. That's like a velocity space. Any of those doesn't really matter, but with a space, if it's three dimensionals, it has a ordered triple. If it's two dimensional, it has a ordered pair. If it's 12 dimensional, it has a ordered 12 or something like that. So you imagine space as the potentially a list of all the individual points that make up the space. Now, you really can't list all of them, but you can figure out formulas and ways of saying it. So you could say, for instance, the space is this left parenthesis, and then all the x's between x equals 0 and infinity, and then comma, and y is equal to all the values of y from 0 to infinity. You could also go from negative infinity all the way up to positive infinity, and that make it a bigger space. But the main thing is you just have a set of values of x and a set of values of y that, when paired together, make a point in space if it's two-dimensional. If it's three-dimensional, you'd have an x, y, and z. But now, in addition to the x, y, and z for three space, or the x and y for two space, you're going to have another set of numbers or whatever. And those numbers could be, for instance, the x, y, and z components of a vector, in which case that would be a vector field. So the electric field, which is a vector field, is the assignment to every point in space a very specific electric field vector. That electric field vector can be specified, like I said, by giving, if it's two-dimensional, you can just give the x and y components, or you can give the magnitude and direction. If it's three-dimensional, you can give the x, y, and z components, or you could do the magnitude, and you sort of need two directions to do that. So like an azimuthal angle and a polar angle. That works fine as well. But that's what the electric field is. So what we're going to do is we're going to imagine Q causes a disturbance, and that disturbance is going to be called our electric field. If we wanted to take the part of the force that is completely caused by just Q and how far away lowercase q is from big Q, then we could say uh, maybe we can use, oh, I want to do that. We can use E is equal to, at least the magnitude, is equal to KQ over R squared. So you could do that, for instance, and you say, oh, well, that's kind of nice because now I have electric field. And obviously, since the force had units of newtons, then the electric field would have to have units of newtons per coulomb, because the only difference between the formulas is it has a q that's been divided out of it. So for instance, if I took the formula for F and I divided it by lowercase q, then I would get the formula for E. Therefore, I expect the units for E are going to be newtons per coulomb. And later we're going to learn that that's also volts per meter, but we haven't learned volts yet, so we're not messing with that. I'm just letting you know ahead of time. So we can consider that to be the disturbance of the field. But the problem with that is if we make the argument that big Q causes a disturbance of the field, then we'd be hypocritical if we didn't say little q does the same thing. So little q's got to do the same thing. So if we take this into account, what we could say is E is going to be equal to the force divided by little q. But that gives us the formula that we want. It gives us the K big Q over R squared, which is great, but it doesn't acknowledge the fact that little q could actually alternate could actually alter the space. I said alternate, but I just meant alter. So little q can actually screw up the space because it has a field that it creates of its own. So what you can do is on an experimental basis, you can sort of think of it as, okay, I'm trying to measure this electric field experimentally, and my calculations allow me to do it up to, say, 2 decimal places. Okay. So then you put in the formula that you think is working for for E, which is F over little q, and you get a result. And then you say, okay, well, what is that result if I do it for a smaller value of Q? And if it doesn't change, even in the second or first decimal place, then you feel pretty confident that you've made Q small enough. If it does change, then you need to make Q even smaller again, recalculate it, figure it out. So what you can sort of think of is we're going to treat the electric field E as the limit as little q approaches zero of F, Coulomb's law, divided by little q, which could mean K, big Q, little q over R squared. Oops, let me do something real quick. I didn't leave a space that I needed to. Okay, so I think that will be plenty of space there. And then I'm going to take all that. Oops, I'm going to mark it with a pen. I'm going to take all that and divide it by Q, but I'm still taking the limit as Q approaches zero. So we can, at each point, figure out what force we get out of it, because evidently doing this implies that the force is equal to Q times E. So if we calculate what the electric field is to 2 decimal places with a particular Q, and then we multiply that particular Q times that electric field, that'll give us a force. If that force is exactly the same as we had before, even to 2 decimal places, then obviously we've made the lower Q small enough. If the lowercase q, or if it's not accurate to 2 decimal places, which is what we want, then we have to try a smaller q. So we try, instead of testing it with a lowercase q, which equals 10 microcoulombs, maybe we drop it down to 5 microcoulombs, try it again. If that still gets us different between the two F's to 2 decimal places, then we go down to, let's say, 1 microcoulomb, and then we go to 1/10 of a microcoulomb, and then we go to 100th of a microcoulomb. And once we get to a place where we get the right answer to 2 decimal places, then we'll say, at least for 2 decimal places, this Q is small enough. Okay. If if we don't go that small, we might still have little problems, but we also might have a later time where we need it to 3 decimal places, in which case we might have to renegotiate exactly what lowercase q is. So that's all I mean by this. In everyday experiments, or excuse me, in everyday life and solving physics problems, you really don't even think about the limit. You just use this formula, and you do it even better than that because specifically you recognize both of these formulas as vector formulas. Okay. It might confuse you taking a vector f and dividing it by lowercase q, but you can also think of that as just 1 over lowercase q times f, and that works. So, yes, fundamentally, it has to be a limiting process that gets us that electric field, but day in and day out solving physics problems, you're just going to use E is equal to F over Q, and F is equal to Q times E. And another way of writing this is E is equal to Q over 4 pi epsilon naught r squared, where now r is the distance from the center of charge of Q, unless Q is a point charge, but from the center of charge of Q to the point in space at which you wish to know the electric field. Okay? So that's really what we're going to do with this formula. Now you've got a whole different way. You can actually calculate the electric field at a point and then find the force by multiplying that electric field times the actual uh, charge. I saw that Jennifer had to split. Do any of you have a question on this? All right. So I'm getting ready to amp it up even further, and it might not be exactly the same way that your book does. I come up with my own formula that's a vector version of the electric field equation that I just did. This one that I boxed off right here, this is also called Coulomb's law. It's Coulomb's law for the electric field. There's later going to be another formula as well that would be Coulomb's law for the voltage. Okay, so just keep that in mind. When I say Coulomb's law, it could be the Coulomb's law for the force, it could be Coulomb's law for the electric field, or it could be Coulomb's law for a voltage, which is a scalar quantity, and we'll discuss that later. Okay, so before I get started, or in order to get started on figuring out the vectorness of this, we need to think a little bit about what the vector direction is for an electric field. We define the direction of the electric field as pointing the direction that a positive test charge would feel compelled to move if it was placed at that point. So what you can do anytime you take a point in space relative to some charge big Q is you just imagine putting a positive charge at that point in space and saying, okay, let's connect a line between big Q's center of charge and that point in space, and then assume big Q is positive, or if it is, say it is positive. If it's negative, say it's negative, and then say which direction would a positive charge put at that point feel deflected towards. So, for instance, if big Q is a negative charge, then the positive test charge at the point would be attracted to it, so the line would go from that point towards big Q. If big Q were positive, the line would go from that point away along the line parallel, or along the line connecting the 2 points. So now that we have that in mind, I'm going to quickly draw a coordinate system that'll be a 3-dimensional coordinate system. I'm going to draw that as my z-axis. This is going to be my x-axis. And this right here is going to be my y-axis, which is a right-handed coordinate system. Remember that, holding up your right hand with your index finger straight out, your middle finger perpendicular to it, and then your thumb straight up, perpendicular to both. Then that should be, your index finger should be like the positive x-axis, your middle finger should point in the direction of the positive y-axis, and then your positive z-axis should point in the direction of your thumb. If it matches that with your right hand, you have a right-handed coordinate system, and life is good. If you don't, it can be really bad, so just don't mess with it. All right, so what I'm going to do is I'm going to imagine a point in space at which there's a charge Q. So right here is my charge Q. Now, this point in space is up some distance above the XY plane, as you can see here. And in fact, it has a very specific X value and a very specific Y value and a very specific Z value. So this would be the XQ, this would be the YQ, and this would be the ZQ. Okay, I know that XQ got written really, really small. Let me make it a little bigger. I don't necessarily need these later, but I wanted to give you some idea of how to picture it in 3 dimensions. So it's X with a subscript Q like that. Okay, now I can define a vector that points to the point Q, and specifically, we're going to treat this Q. I wrote it as Q. I really shouldn't write it as Q. I should write it as DQ. So let me do that because I'm going to be using this formula predominantly for doing integrals. So with that in mind, I'm going to call this charge DQ. And of course, that means these are Y sub DQ, Z sub DQ, and X sub DQ. And I'm just saying that, hey, this is going to be a infinitesimal charge element that we could use as an integrand. Okay. Now, the vector that points from the origin to that charge DQ, I'm going to call that vector R sub DQ. Okay. Now I got to figure out somewhere in space what the electric field is. So I'm going to choose a point in space, and this time I'm going to choose it as if its color is a nice purple. So I'm going to say this point, I'm trying to make it really significantly different. I think it might be best to, that's not going to be very good. Maybe this will be good. Okay. So I'm going to say this is point P at which we wish to know the electric field. Now, if I'm trying to show where in the coordinate system this is, then I have to go back here and connect this like that. And then, of course, I have to connect it to the y-axis, which would put it right here. And I have to connect it to the x-axis, which would put it right here, so on and so forth. But the main thing is now we have an entirely different vector that points from the origin to locate the actual point P. So hopefully I've drawn it well enough, just barely, to miss that. Okay, now this vector again goes from the origin to the point P, so I'm going to call it R sub P. Now, if we go on the assumption that Q or DQ is positive, then we know we want the electric field vector to point from the end of RDQ, where that blue dot is, to the end of P, R sub P, where that purple dot is. So we really need that as the direction vector. So the direction vector I'm going to write here, I'm going to use green, and it's going to go from here to P. So this vector is called, we can actually call it DQP. That would be one way we could do it. But we could also call it something different. But what I want you to realize is that it's gotten from actually doing a subtraction. And the subtraction is RP minus RDQ. So it's going to be RP minus RDQ is that vector. And therefore you might wish to call it PQ. That's fine too, because you don't really actually have to have the double bars for the P or the D for the Q. The main thing is you need to know the order, and the order is P minus RP minus DQ. So now that we have that, we can go ahead and write Coulomb's law for the electric field as dE in a vector form now is equal to dq over 4 pi epsilon naught. Now, remember the distance between Q and P is that vector RP minus RdQ. So I'm just going to put the magnitude RP minus RdQ. That's the magnitude. And it's a 1 over r squared law, right? Because you can see the exponent of 2 here. But the problem is, to make this a vector, I need to multiply the whole thing by a vector. So the ideal scenario would be if I were to take this vector right here and make a unit vector out of it. Well, the way you make a unit vector out of a vector is you take the vector and then divide it by its magnitude. Okay? So instead of putting a 2 down here, I need to put a 3 so that it will have 1 to counteract the magnitude of the vector that's in the numerator. So I now say RP minus R dq. That's the actual vector. And to make it a unit vector, instead of having a 2 down here for the exponent, I'm going to have a 3 down here for the exponent. And that is our formula for the vector electric field. I've actually done several of these problems online. I would like you guys to go ahead and look for electric field due to, and do a search for this part, infinite. You probably can just do a search for that much, but you're looking for an infinite line of charge. Okay. That's the next problem I'm going to solve. You guys are free to go, but like I said, that's the next problem I'm going to solve for you. I might do it in a video I make for tomorrow. Hopefully, y'all have already seen that TCC canceled classes for tomorrow, Wednesday. So, and that's Wednesday, the 19th of February. 2025. So go ahead and check that out to look for any other videos on my YouTube channel. But other than that, you're free to go. I'll wait for the last person to leave in case anybody has any questions.
All right. See you, Professor. Thank you.
Thank you.
Thanks, Matt. See you, Josh. See you, Matt. Okay. So I would like to work this problem now, but I think I'm going to have to wait till later. So let's stop sharing and I will call it a day. Bye, everyone.